Tamam. Okay, so last week we had finished the discussion of vectors. We said that, okay, vectors are the things that we use to describe the position and the motion of objects in 2 dimensions and 3 dimensions, because we need 2 information to specify the position of an object, at which direction is the object, and at what distance. So we need these 2 information, and the mathematical objects that carry these information is what we call vectors. And now we were discussing the circular motion. Now today I will start by repeating the circular motion, but before that, do you have any questions about the vectors? Do you understand the components of vectors, the manipulation of vectors, addition, subtraction, multiplication? Okay, so let's start with uniform circular motion. Let's review it. Okay, so first let's define what we mean by uniform circular motion. We didn't really pay that much attention to what we were discussing. One is, so circular just means that it's going around the circle. Uniform means that the speed is constant. So the speed doesn't change. So basically, for example, this motion is more or less uniform circular motion. This one is not. We will see why not. Because in this motion, although the motion is circular, the speed is not constant. So that's why this motion is not uniform circular motion, whereas this one, the horizontal motion, is uniform circular motion. So we know that the speed is constant. So does that mean the acceleration is 0?
Yes. No.
Yes? No?
Because its velocity changes.
Why do you think it's 0?
Speed is constant.
Okay.
It is constant. Acceleration is 0.
How do we define acceleration?
Like acceleration is changing velocity. Delta x over delta t.
Now, delta x over delta t, or in three-dimensional case, okay, delta v over delta t is what we define as acceleration. Now, let's say this is the average. But it is the change in the velocity, not the change in the speed. This change in velocity divided by the time it takes. Now, velocity has two information. It has the direction information and the magnitude information. The magnitude of velocity is what we call the speed. So speed constant just means that the magnitude of the velocity vector is constant. But nevertheless, the direction might be changing. So if the direction is changing, then it's a completely new vector, because you see, vector has two properties, the magnitude and the direction. If any one of these change, that means the vector is changing. So in this case, although the speed is constant, it's not necessarily zero acceleration motion, because the magnitude, the direction might be changing. So if you look at the trajectory of the object, now this is what we call the trajectory. It is the collection of all the points that our object will be or has been. So if you have the object over here, it is doing uniform circular motion. Its velocity, let's say, is pointing in this direction. And at a later time, it will be somewhere over here, and the velocity will be pointing in this direction. And the velocity and the radius vector, let's say this is the radius vector, this is the velocity vector. They are always at 90 degrees. So how can we prove that they are always at 90 degrees? How do we know that the velocity vector and the radius vector is always at 90 degrees? Well, that's the definition of being perpendicular to the radius vector. So how do we know it's a tangent?
We can take conditions over very small time amounts, and when we show the change in vectoral change in position, we say that the velocity always nearly perpendicular to radius.
Is it nearly or exactly? My claim is that the velocity vector is always perpendicular, exactly perpendicular to the radius vector.
I get exactly.
In a real situation. How do you know that it's exactly? Well, your friend started on the right track. So you see, how do we define the velocity? The velocity was delta r by delta t. Of course, we take the limit as delta t goes to 0. So we just take the position of our object at two nearby points. So let me just exaggerate the drawing a bit. Let's say this is the center of the circle. This is our circle. At some instant, this is the position of my object. At the next instant, it is somewhere over here. So this is the initial radius vector. This is the final position vector. What is the displacement vector? It's pointing downward, upward. It started from here, it went there. So this is the displacement vector. This is delta r. Now the velocity vector, average velocity is proportional to this delta r, divided by delta t, which we took to be positive. So because this is an initial time, this is the later time, so delta t is positive. So we see that the direction of the velocity and the direction of delta r, they are the same. They point in the same direction. Their magnitudes will be different, but they point in the same direction. Now, this is the angle between delta r and the radius vector. Now, this is an isosceles triangle because it's making a circular motion. So this side is equal to this side. This angle, let's call it theta. So this angle over here is pi over 2 minus theta over 2. This is the angle between the radius vector and the velocity vector. So as your friend said, the average velocity vector for very small times is almost perpendicular to the radius vector. But we are talking about here the instantaneous velocity. Now, when we are talking about instantaneous velocity, we take this theta smaller and smaller and smaller. Now, as theta becomes smaller and smaller in the limit that theta becomes 0, in this limit, when time goes to 0, theta also goes to 0. So this angle over here is 90 degrees in that limit. Okay, any questions on this proof? Okay, so this angle is 90 degrees. Well, we have another way of proving exactly the same thing. Once you get used to vectors and calculus, we are told that it is a circular motion, so the magnitude of the position vector is always the same. So the position vector squared, which will be, okay, how do we define this scalar product? The product of the magnitudes, which is the radius squared, times cosine of the angle between the two vectors. Well, the angle between a vector and itself is 0, so cosine of 0 is just 1. So this position vector squared is always equal to the radius of the circle squared, which is a constant during the motion. Now let's take the time derivative of both sides. Now if we take the time derivative, well, it's just like ordinary derivation, the vectors. I mean, you can think of in terms of the components if you like, but you can also think of it as if it's an ordinary differentiation of the square of something. So how do you take its derivative? It will be 0 because r squared is constant in time. It doesn't change during the motion, so its derivative is 0. Now the derivative of the left-hand side, well, if it was a one-dimensional motion, d by dt of x squared, this would have been 2x dx by dt. Just use the chain rule. I mean, you can use the chain rule for each one of the components of this r squared. Now let's see. R squared, we also know that the scalar product, we can also write it as, we just multiply the corresponding components and sum them up. This is x squared plus y squared plus z squared. If you take the time derivative, this will be twice x dx by dt plus twice y dy by dt plus twice z dz by dt. I'm just taking the derivative of each one of the terms. Yes, questions? Okay, the position vector, we write it in this form. The x component plus the y component plus the z component. I don't know what they are, x, y, and z. But I just assume that I chose some coordinate axis, the x, y, z components, and my object is doing circular motion. So the x, y, and z component as the object is rotating will be changing in time. How? Well, we can write it down once we specify which coordinate system we choose, but we will not need it. The only thing I will need is that whatever the motion is, x squared plus y squared plus z, whatever the coordinate axis is, x squared plus y squared plus z squared will be 0. That is the distance from the origin. I'm assuming that my origin is at the center of the circle. So this is why I write this first line.
Why is your T-square?
This one. Okay. Other questions? Okay, let us rewrite this thing. dx by dt is nothing but the x component of the velocity. Twice x vx plus y. Well, dy by dt is the y component, vy, plus z. dz by dt is nothing but the z component of the velocity. So this is the x component of the position multiplied by the x component of velocity, the y component of position multiplied by the y component of velocity, the z component of position multiplied by the z component of velocity. So here I have two vectors, the position vector, this one, and the velocity vector. I'm just multiplying the corresponding components and summing them up. But this is nothing but the definition of scalar product. So, okay, this is dr by dt. And we had already seen that since r squared is constant, its derivative with respect to time has to be 0. So this should be equal to 0. Now I have two vectors. Their scalar product is just 0. So what can I say about these vectors? They are perpendicular to each other. So this position vector and the velocity vector, they have to be perpendicular to each other. Now you have two different ways of proving the same thing. So either you can look at this geometrical interpretation, or you can look at this more mathematical derivation. Well, you see, playing with taking the derivative of vectors is quite similar to the taking derivatives of ordinary functions, in the sense that you could have just, starting from the beginning, you could have said that by just using the chain rule, derivative of r squared is nothing but twice r times the derivative of r, what we have done over here. The only difference will be, it's not ordinary multiplication, it will be scalar multiplication. That's the only difference. So although currently we are just writing all these to show this, that the derivative of r squared with respect to time is equal to twice r dot v, in a couple of months you will be able to write this just in a single line. So it will take much shorter. Now, any questions on this derivation? So now we know that the velocity vector is perpendicular to the radius vector in uniform circular motion. Now, another way of looking at the same thing is that you could have said, okay, so let's just imagine that we have some axis moving in that, along that direction. Since its position along that direction isn't changing, shouldn't change, because if its position along, for a very small amount of time, its position along this axis shouldn't change, because if it does, it would just mean that it's getting away from the origin, that it is not moving on a circle. So its position on that axis shouldn't change for very small times. That means the velocity along that axis should be 0. But that is nothing but the component of velocity along the radial direction should be 0. That's another argument that you can make to show that the velocity vector has to be perpendicular to this radius vector. Okay, so we know the velocity vector now, we know its direction. Well, of course, given a circle, just a trajectory, we have to be told in which sense the object is rotating. Is it rotating in the clockwise, counterclockwise sense, or the clockwise sense? That would change whether it is pointing upward or downward. So we are assuming that we already know that information, and our object is rotating in the counterclockwise sense. So that the velocity vector at this point will be pointing upward, at this point it will be pointing in that direction. Now let's calculate the acceleration. What about the acceleration? Okay, acceleration is a vector, so we have to find two quantities. We have to find its magnitude and we have to find its direction. And if you remember, the acceleration we had defined as the change in the velocity divided by the time. So this is how we define the acceleration. So we have to pick up two successive times, calculate the change in the velocity. Its direction will give us the direction of the acceleration and divide it by the time it takes for that change to happen. So again, let's just take two successive times. Initially, this was the position of my object. And at the next time, this is the position and this is the velocity. This is the initial, this is the final. And let's again call this angle theta. So how long does it take for my object to move from here to here, assuming the speed is constant? This is called constant speed V0. How long does it take to go from here to there to cover this angle theta? Somebody else? Well, let's see. That's correct. What is the length of that arc? This length. R times theta. Let me call that L. L is the length of that arc over there. Do you remember this? Any questions on this? Well, this is basically how we define the radian degrees. So theta is nothing but L over R. This is how we define the radians. You take a circle, you take your angle with the angle at the center, you measure the length of the arc that that angle sees divided by the radius, and that is the angle in terms of radians. So any arc length is nothing but the radius multiplied by the angle in terms of radians. So the time it takes, let's say delta t, is nothing but this arc length, that is the distance that my object covers, divided by the speed. This time it's not the velocity, it's the speed, because we are talking about the distance covered at constant speed. We are not talking about the displacement vector. The displacement is not L. It is a bit smaller than L, divided by V0. This is our delta t. Now let's look at how much did the velocity change. Let me again exaggerate it a bit. So initially, this is my velocity vector. And after it has rotated by the angle delta theta, by the angle theta, this is my other velocity vector. This angle over here is theta. And this vector over here is my delta v. And let's also consider this arc. This is the arc of the circle. Well, since the initial velocity and the final velocity, they have the same magnitude, this distance is equal to, this length is equal to the other length, my motion is, and my object is rotating around the circle, the only thing that will happen to the velocity vector is just, it will be just changing its orientation. Initially it was pointing upward, the next time it will be pointing in that direction, and in that direction, in that direction. Since it's uniform, the magnitude will not change. So if we just imagine a circle with center over here, so my velocity vectors will all go along that red curve, which is just a part of a circle of radius v0. My velocity vectors, I started here, they are rotating, they are changing their direction without changing the magnitude. So they will just go over a circle. Yes, questions? Questions, yes. You. So which part did you miss? Which part did you miss? Okay, which part is not clear? On the last page, okay. This one. Now this is how I define it. What I will ask you is, I can see that none of you is really following. You couldn't wake up yet, it's just 8:40 in the morning. But if you don't tell me which part you missed, I cannot repeat it. I don't know what to do. So if you miss a point, just let me know that you have missed it. Not just by your faces, but also by asking questions so that I can repeat, because everything will be built upon one another. So if you miss one point, you will miss the next point also. Now let's start with this one. Now how did we define vectors? We said that, okay, if I want to talk about your position, first I have to choose some reference point. Any point will do. I can choose this point. I have to choose some directions as my axis. I can say, okay, this is the x direction, this is the y, this is the z. Then I have to tell in each direction how far should I walk to reach your point. So I have to walk something like 3 meters in that direction, then followed by 3 meters in this direction, plus some 20 centimeters in this direction to reach your position. So this x, y, and z, these 3 meters, and 20 centimeters are what I call the x, y, and z components of your position. And this is how I show it. I choose some x, y, and z directions, and in each one of those directions, I tell you how much I should move to reach your position from the reference point I chose. Now, we are studying circular motion. I just imagine that, okay, let's put the reference point at the center of our circle. Now, my reference point is the center. I didn't really specify what is x, y, and z, but I can just choose any one of them, any set of x, y, and z directions. And using those axes, I should tell you these 3 numbers to find the position of my mass. Those are what I call the x, y, and z components of the position. So this is why I write it in this form. I don't really know what is the x direction. I didn't specify it. I will not need it. The only thing I will need is that the origin is the center of my reference point. Since the origin is the center of my reference point, I know that my object, the distance of my object from the reference point is constant. The distance is x squared plus y squared. The distance is r squared, that's the magnitude of the position vector squared. And if I have this decomposition, it's equal to x squared plus y squared plus z squared. Then I just take the derivative to obtain this expression. On the other hand, I know that this distance is 0, so this should be 0. Whatever, I don't know what x, y, and z is. I didn't write their expression. I don't need them. I only need this expression. Whatever the x, y, and z are, if the object is doing uniform circular motion, This should be satisfied. In fact, if the object, even if the object is not doing uniform circular motion, here I didn't assume that V is constant. The only thing I assume to derive this result is that the radius vector has a constant magnitude. So as long as my object is moving on a circle, whether uniform or non-uniform, the velocity vector has to be perpendicular to the radius vector. This is true also for non-uniform circular motion. In the case of non-uniform circular motion, of course V will change, but this just shows me that its magnitude will change. Its direction will again be always perpendicular to the radius vector. Okay, any questions on this part?
Hocam şimdi burada biz dairenin iki büyükresine de velocity için eşitledik sağ tarafta.
This one, okay.
Önceki sayfada da yer değiştirmek için, delta R için aynı şeyi söylemiştik.
Okay.
O zaman şunu söyleyebilir miyiz? Delta R'la delta R, delta V eşitli diyebilir miyiz?
No. You see, delta R is equal to delta V. What is the unit of delta R? What is the unit of delta V? So they cannot be equal. So what we are actually doing, we talk about the position. That is, okay, let's just imagine this is my mass. It is doing some circular motion. I can talk about the position vector. That will be something pointing in the direction of where this object is. And the magnitude will be equal to the magnitude of that one. So I can imagine the collection of all these vectors. And we know that since it's doing circular motion, and I put my reference point at the center of this circular motion, if I trace the endpoints of these vectors, they will just follow this circle. Okay, so there's a circle over there. That is in position, what we call the position space, so that if we just show the positions of my object at different times, it will be a circle. Now the other thing, this one over here, is what we can call is a vector space. But let us also define what we mean by space. Now whenever we call space, we will usually mean, in the mathematical sense, it's a collection of vectors. That's basically what we mean. If you have a collection of vectors, then, and you can add and subtract and multiply them by numbers, etc., that's what we call space. If you talk about the position vectors, you just imagine all kinds of possible position vectors. That is what we, in everyday life, what we call space. But we can also imagine all kinds of possible velocity vectors that an object can have. Well, that is what we call a velocity space. Now, this one is in position space. Every point on this circle is the actual position of my object. This one is what we call the velocity space. So I imagine the velocity vector. Well, if the object is over here, this will be the direction of the velocity vector. And I just trace the endpoint of the velocity vector. So it will just also, as my object is rotating, the velocity vector will also rotate. I can just imagine all the endpoints of the velocity vector. But we know that the magnitude is constant. So at least in this collection of velocity vectors, I can still imagine a reference point. I can gather all the endpoints of the vectors together. They all start, I can imagine they all start from this point. I just move them. If I move them all here, the magnitude of this vector as it is rotating, it is just constant. It doesn't change. And that is what we call a circle. Not in real space, not in position space, but it's a circle in velocity space. Now, just like you cannot compare quantities of different dimension, you cannot compare quantities of different spaces. You cannot compare a vector in position space with an object in velocity space. So that's why we cannot write this thing. These two things live in different spaces. But just imagine, just make this imagine. This is the initial velocity, the final velocity. I just moved all the velocity vectors so that their endpoints coincide. And then since their length, which would correspond to their magnitudes, is the same, the endpoints will just trace a circle. This is where I'm now using the fact that it's a circular motion, but now it's uniform circular motion. And hence, this side is equal to this side. Other questions?
Are same shapes?
Both of them are circles. But of course, they don't have the same size. The radius of this circle is r. The radius of this circle is v0. It's the magnitude of the velocity vector.
Okay, in another one, can you see that looking at the first illustration, this one,
This one, okay.
yes, appears as if there's a change in distance as the velocity, the rotation of the velocity changes. There's a change in distance. If you look at that towards the center of the circle.
Well, if there's a change of distance to the center, that is the lack of my artistic capabilities. So I couldn't draw a perfect circle. I couldn't identify the center point. So just imagine this is a perfect circle. So all the points on this circle are at the same distance from the center. There's no change in the distance.
When you look at this, virtually, when you look at the diagram, virtually it appears as if there's a change in distance to the center.
No, but it just appears because, as I said, I couldn't draw it properly. But in the motion that we are studying, this one, there is no change because the distance is fixed to this length. It's always the same. So distance doesn't change. But it looks as if this distance from here to here is shorter than the distance from here to here, but I couldn't draw it properly. That's the reason. You have a question?
Yeah, actually, I have one question. Think about the final initial, both of them the same. Are 10 meter.
Okay.
BF 10 meter, ve initial 10 meter.
No.
What will happen?
You see, V final cannot be equal to 10 meters. V final is a velocity. Okay. Okay, so you have a 10-meter radius, object moving in a 10-meter radius with a speed 10 meters per second. Fine. So, if the units are this different, you cannot really talk about the 10 being equal. 10 in 10 meters and 10 in 10 meters per second, you cannot compare them. You see, you could have as well chosen not second, but another unit for time measurement. And then that 10 would just be changing. Other questions? Okay, so what is the length of this arc? Yes, this radius is V0. So the length of the arc, let me call it LV, is equal to V0 times theta. Again, it's the velocity space, but nevertheless the definition of the angles will be the same. This LV over here, what's the unit of this LV? It's meters per second. It's not, although I use the symbol L, it's not meters, it's meters per second, because this is the distance in what we call the velocity space. Now, what about the magnitude of delta V? Because we want to find the acceleration, both the magnitude and direction. So let's first study the magnitude of the acceleration. The magnitude of the acceleration will be the magnitude of delta V divided by delta t. So what is the magnitude of delta V? Well, we can use cosine theorem, but then what do we do with cosine theta? Now okay, there are means of doing it. You will be doing it toward the end of the semester, but we might have an easier way of doing it.
Can you say that LV and delta V is equal in this case?
They are not equal, but they are approximately equal. Of course, delta V is shorter than LV. If theta is large, delta V will be much shorter than LV. But for very small LVs, for very small theta, the difference will be for smaller and smaller theta, the difference between delta V and LV will go to 0. Let me write it in this way. In the limit as theta goes to 0, this will be 0. They will have the same length. Now, of course, writing this doesn't mean that much because delta V will go to 0 and LV will go to 0, 0 by 0. But even this one will go to 0. So this will be 0, this will be 0, but the ratio will also be 0. So I can approximate delta V by LV. So delta V is approximately LV. Now delta V by delta t, the magnitude of delta V by delta t will be approximately LV divided by delta t. Now we had calculated delta t. Delta t is L over V0. This is L over V0, LV. Now we had obtained LV is V0 times theta. We had obtained L is R times theta. So theta has just become 0, cancel. So this is V0 squared over R. So this is the acceleration. Well, it is independent of theta or independent of delta t. We calculated this for very small delta t, but the final expression is independent of delta t, so we can just take the limit as delta t goes to 0, and it will still have the same value. The magnitude will be limit as delta t goes to 0, delta v by delta t, which is nothing but v0 squared over r. Okay, the magnitude of acceleration is constant. Is it a motion with constant acceleration? Yes, no?
The point where the acceleration will point to different directions.
So you are saying no? Okay. Anybody who wants to say yes? Your friend is saying that the direction of acceleration will be changing, so it won't be a constant acceleration. So we have shown that the magnitude of acceleration is v0 squared over r. Since it's a circular motion, r is constant. We also know that it is a uniform motion, so v0 is constant, the speed is constant. So the magnitude of acceleration is constant. is it a motion with constant acceleration? Your friend has said that although the magnitude is constant, the direction of acceleration is constantly changing, so the acceleration vector is not constant. It's not a motion with constant acceleration. Do you agree with your friend? Do you think it's a motion with constant acceleration? Okay. Anybody who disagrees? Okay, your answer is correct. So it's a motion with varying acceleration because, as your friend points out, the acceleration vector will be changing. Now, what is the direction of the acceleration vector? How? Why? Why?
Let me show the displacement, sorry, the change in vector, change in velocity vector, like this one. This is perpendicular to, for example, the initial velocity.
Why not the final velocity?
Yes, final velocity. I just, for example, and then we show the force on the circle, then the point, then we draw the delta V vector on first circle. We see that it is pointing center.
Okay. That's correct. It's toward the center, but you see, it is pointing toward the center for the instantaneous acceleration, not average acceleration. If you remember, on Thursday we had also done an example where we discussed the average acceleration. Now, in the case of average acceleration, you cannot say that it's pointing toward the circle, because you see, the vectors, you can just move them around. So I can move the acceleration vector anywhere you want. So the point where it points might be changing. If you put the acceleration vector at the point of your object, in that case it is pointing toward the center. Because if you look at here, this angle over here is, for a finite value of theta, it will be almost 90 degrees for a small value of theta. And when you take the limit theta goes to 0 or delta t goes to 0, then it will be almost exactly 90 degrees. Now, our initial velocity vector is pointing in this direction. The acceleration vector, which is in the direction of delta v, is pointing perpendicular to that, and that is in this direction. So if you are sitting over here, and if you have a vector pointing in that direction, perpendicular to this velocity vector, it will point towards the center. So that's why it's pointing towards the center. Now, if it is over here, again, you can just repeat the same thing. This is the final Vf, so you just take a next time, draw another velocity vector, it will be pointing in this direction. Of course, you will take the limit that the angle between the two vectors will be 0, and when the object reaches this point, the acceleration vector will again be pointing in that direction, which is again towards the center. So the acceleration vector, as the object moves around this circle, will be always towards the center. So this is constant, and the acceleration vector points towards the center. Now, any questions before you go for a break? Okay, before you go for a break, let's start with a quiz. So remember, you should hand in one full page, whether your page is large or small, I don't care. But bring one full page, don't just tear it into smaller pieces. And everybody brings their own quiz. Don't bring your friend's quiz. When you finish the quiz, you can go for a break. Just write the answer. The quizzes are supposed to be very short, easy to answer, and easy to read. And once you hand in your quiz, you should start chatting when you go out of the classroom. Quiz bitmedi henüz.
Kalmıştım da şöyle yaptım, sadece bir şey soru falan yazdım sonra.
Okay, your time for the quiz is almost over. You should bring your quiz